Hello, my name is Max, and I'll give a talk on Riemannian optimization on DataFest. The talk will consist of 3 videos. The first video will be about connections of traditional optimization and Riemannian optimization without very much details. The next video will be in-depth introduction with mathematics in what is Riemannian optimization and how is it connected with real world. The last video will be the going through the code of GeoOpt to implement Riemannian optimization in PyTorch. Let's go ahead. So, why do you need Riemannian optimization and how you can use it in your work? And we all use optimizers like Adam, SGD, AdamW, IMSGrad, whatever, without proper understanding of how they're working. And of course there are some papers that describe the details of the implementation and there are open source libraries, but we don't really need to care about how it's working. And the same goes with Riemannian optimization. You only need some well-defined task where this Riemannian optimization is applicable, and without proper understanding of why is it working, you can use already implemented algorithms in open source libraries, and there is no problem in doing that. If you don't want to listen to a lot of mathematics and want to just use the code to run your examples and improve your models, or maybe you're already familiar with Riemannian optimization, and that's wonderful, then you can go to GitHub repository GeoOpt, that is an open source library on Riemannian optimization, and it offers you a lot of possibilities you can use in PyTorch and build it in your favorite model or framework for running experiments. However, if you want some math, then welcome, we'll go ahead. So, when do we need Riemannian optimization? The first thing you might think is the constraint problem. And what type of constraint is actually useful to consider when we choose between projective optimization or Riemannian optimization? For projective optimization, you can use whatever constraints, but for Riemannian optimization, your constraint should have some structure. And in this case, the structure is the smoothness of the constraint. Like on sphere, we have the smooth surface, or it might be like some matrix manifold, and we might want to relax the problem. For example, the famous matrix manifold might be orthogonal matrix or probability simplex, or it might be the matrix that is doubly stochastic and that is used to match key points. And all these examples can be unified in terms of Riemannian optimization. The sphere, the orthogonal matrix, and Bikov polytope, that is this doubly stochastic matrix manifold, and many others. So you can't actually enumerate them, but they all have smooth constraints, and it's very useful to apply proper methods that take it in account. Traditional optimization tools that use projective gradients don't really use adaptive term in its full power. But when you use Riemannian optimization and you have a predefined structure, you can use these adaptive methods to their full power, because you can compute this adaptive term in closed form, you know how to update it, and so on. Another intriguing example that is probably not achievable with projective gradient or other methods is HMC with constraints. So for example, you might want to use MC methods on matrix manifolds. doubly stochastic matrices, or Stiefel manifold, or sphere, and so on. And you have your probabilistic model, and you want to create posterior samples out of this model. And traditional tools don't offer this possibility. But in Riemannian optimization tools, you can build your HMC algorithm quite easily and run posterior sampling. And that's actually great and already used in several research papers. What else we can use besides Riemannian optimization? For example, you can use reparameterization, and that's quite useful approach when you can express your constraint parameters from unconstrained domain. Another thing is projection, like on the picture on the right, where you project the unnormalized vector to its normalized version. And these two approaches differ in terms of adaptive term really makes sense only when you do reparameterization, because you don't remove the degree of freedom. In this case, also you can use HMC, and this is quite a nice approach if you can do that. If you can't, and you use projection, then adaptive term doesn't really make sense, because the degree of freedom is incorporated in your adaptive term on unconstrained domain. And this projection may be hard to differentiate through, like on Bikov polytope you run sinkhorn iterations, and so on. So this is quite problematic. So let's look at IMS grad in Rn. And IMS grad is a bit improved version of Adam, but on this example we can really see everything that we need to consider when building any algorithm that has adaptive terms, that has momentums, and other things. So let's start. Of course, we have a function that is differentiable, and we assume that it's possible to compute its gradient. After the gradient, we should take care of momentum. So we combine gradients accumulated from previous iterations with this new gradient. In this case, it's just exponential averaging. The next thing is adaptive term. And for adaptive term in Rn, we use second moment of the gradient to scale gradients properly so they don't explode, and the most promising directions are valued more. And the final gradient step. And that's all fine. But let's go to Riemannian optimization and Riemannian version of IMS grad. Without going into details, it all looks very similar. We have the same gradient, but in the second case it's Riemannian gradient. We'll talk about it later. Similarly, we should combine moments accumulated from previous iterations, but there will be a problem, and you see it's in the end we should take care of momentum for a number of reasons. Adaptive terms are also computed similarly, but now the adaptive term is dependent on the point you stand. And the optimization step. In this case, exponential map is used, and exponential map is similar to what is going on when we move the point towards the most promising direction, but we do it smoothly. After this walkthrough, there were some missing points we don't talk in detail. For example, how to work with gradients, because gradient and the point, it's very different. They are different creatures. Something is direction, another is location, and how do we combine them? Why do we use summation or subtraction in Rn case. The next thing is the computations that depend on actual points. For example, the adaptive term is computed depending on the point we're standing on, and the reason why is it so is vague, because in Rn we didn't really care, just computed second norm. The momentum, as we remember from Euclidean optimization, we just accumulate gradients, do exponential averaging, and that's it. And in Riemannian optimization, there was an additional operation to move momentums to the next points, and why is it for, and so on. And the final update, why can't we use summation or subtraction or whatever operation? Why do we need the additional function exponential map? So these questions are the core questions to do research in field of Riemannian optimization and have a better understanding of what's going on. And in the next video, we'll review it in very detail.